Good morning to our colleagues from the Fish and Wildlife Service Southeastern Coastal Program. This is a presentation of the National Oceans Applications Research Center. From our opening slide, you can see that our theme, our applications research theme, is associated with coastal work and coastal restoration. And we're focused on three applications research themes. The first one is working waterfronts. The second one is nearshore benthic habitats, and the third is coastal habitats, specifically focused on forested and non-forested wetlands, shorelines, and barrier islands. Okay. Next. In our first example, we'll show you some projects that we're using to focus attention on working waterfronts. This is an image of our unmanned testbed system, the Seaworker 5 from ASV Global. And we use this system to integrate and test four specific systems that we needed to understand before we went further with smaller and larger systems that we'd use for a variety of things. We had to make sure that our sensors were working the way we wanted them to work to do precision environmental monitoring. We needed to make sure that our software set was integrated. Our challenge here in working waterfronts is to turn around precision bottom maps in less than 24 hours. And that requires advanced positioning sensors, unmanned systems operation, and an integrated software suite. And we're able to do so with this system. Wanted to show you an example of a fly-through that shows a combination of co-registered multi-beam echo sounder data, side scan sonar data of the Gulfport turning basin and the Gulfport channel. Now, the details here are important because this is the first time they'd seen such an image of their site, of their harbor, and of their channel. And over time, we're able to provide these measurements precisely and update them routinely so that we can get an idea of where precision dredging needs to take place, and we can certainly map any obstacles in the channel as a result of a storm event. And that was the hardest of our requirements, to be able to turn these data sets around in less than 24 hours and provide enough data to reopen the channel after the port's been closed as a result of Coast Guard closure. Now, that example led us to our work in shallow water benthic habitats. We were able to team with a group out of Stuart, Florida, Sea Robotics. This is a Sea Robotics Surveyor M1.8. It's about 6 feet long, 3 feet wide, and it's built around our favorite co-registered sensor, the EdgeTech 2205, which is the same version that we just showed you on the Seaworker 5. It's just without a housing, and it's housed within the sponson, left sponson of this vehicle. But this is our workhorse in shallow water environments. It'll tolerate about 2 feet of seas. We like to work in flat water because the sensor has a motion compensation unit built into it. We're able to provide precise measurements in about 2.5 feet of water is ideal for us. This system can operate up to 60, 70 feet in depth. It just doesn't like a disturbed sea state. And so we're using this system to do our smaller working waterfronts, and we have some examples of those too. And also, we're using this system to do our nearshore benthic habitat, specifically oysters, oyster restoration, seagrasses, and hard substrates for recreating or restoring barrier islands. This is a quick overview after Hurricane Zeta. We collected this the 10th of November, and this is some detailed aerial imagery that we're using as a backdrop for our hydrographic data. This is an example of the kind of bathymetry that we can provide with our survey system. And that image shows them that their clearance depths are adequate for their craft to enter and exit the harbor. This is an example of the side scan sonar plus the LiDAR instrument that's on our Sea Surveyor. And you can see the details on the bottom. And from this map, we derived a debris map that our engineering strategic partner in the city of Bay St. Louis were interested in mapping. They need this detail to apply for emergency funds to clear the harbor. And of course, before you can clear it, you need to know where the debris field is, and this is a precise location and description of that debris field. I wanted to show you this as just a precursor to some of the examples we'll show you later. This is a three-dimensional airborne system of a floodgate in New Orleans. We used our photogrammetric mapping camera that we fly in concert with our LiDAR instrument on our unmanned airborne vehicle to give us precise measurements, and I wanted to set the stage for some other work we're doing. But this example shown here begins to introduce the concept of a seamless three-dimensional view of the bottom all the way to the surface, and that is going to address some of the stringent requirements for monitoring coastal restoration work, specifically barrier islands and shorelines. This is one of our test sites that we work cooperatively with the Nature Conservancy. You see outlined in purple the permitted area for oyster restoration. The blue rectangle represents the area that they had previously developed, and the orange one is the orange areas that which we surveyed. Okay. Now this is an idea, give you an idea of the data that was available to them to examine the oyster restoration project that they started about 10 years ago in this area, and we needed to answer a simple question from the National Fish and Wildlife Foundation. They were prepared to grant more resources to this area if we could answer the question, how do you know it's still there? And so we were able to answer that question in great detail for the Nature Conservancy and NIFWF. Okay. This is an example of our bathymetric survey data. This was gathered on a day when we had about 3 feet of clearance over the reef. This gives you an idea of the precision. This is of the system. We were mapping this area in about 25 centimeter excuse me, grid. And the example points out how valuable it is to have co-registered on one sensor, a side scan sonar and a multi-beam echo sounder, so that the post data collection processing is simplified so much and we could turn the data around very quickly. This is an example of multi-beam and side scan merged over the area, and the redder areas are those that are the shallow areas of the reef, or the areas with the most reef relief, and that turned out to be a valuable data set for them, and that's what they used to acquire the new grant. Now this is a follow-up mission on the same area. Some limestone culch was deployed, and you see here the example of the extension of a USGS quarter quad mapping reference out into the water. These are 100-meter grid cells, and each one has a unique identifier, and we use them to keep up with all of our projects and to monitor change over time within a specific area. This is an image of bathymetry, of the culch deployment. The next image that you'll see is an image showing the side scan sonar imagery, and you see you have much more returns of hard surface, and you get an idea of the pattern of the barge deployment of the limestone culch. And we superimpose that on the previous information so that you can demonstrate, or we can demonstrate, the trend analysis over the area. And one of the things that is so important to oyster restoration, or any other habitat for that matter, is that to manage it, restore it, or recreate it, you need to know where it is, and you need to know how it evolves over time. And with this system, we're able to track it, precisely measure it, come back to the same point, run the same lines each and every time, and provide some very precise change detection analysis of any shallow water benthic habitat. Another site we had over in Biloxi, at the mouth of Biloxi Bay, a similar material was deployed, but it was deployed in a pattern. You begin to see an example of our data set. This deployment was based on a barge that anchored in one spot and circled around the circled around one anchor point, and you can see it within our 100-meter grid reference system, and it looks something like a crop circle. This is an example of side scan data, give you an idea of the picture, the relief on the deployment. And this is a close-up of that material, and you can see the undulations within that Cults deployment. Now, we're excited about this particular example. We were asked to look at an historic reef off the shore in Ocean Springs, and we're able to see you see the lighter areas of the hard substrate returns. Those happen to be under about 10 inches of silt. So that answers a couple of questions for our stakeholders. One, if we don't have oysters there, do we have hard substrate that we could build upon? And we can certainly map the covered substrate. And then secondly, we were able to map that substrate within our reference site, so we'll help them with deployments later. That's a close-up of the area. This is also important. We're able to find hard substrates in and around and near some areas that we're considering for beneficial use of dredge material and to restore some barrier islands. We have an example coming up of some work that we're doing on one of those. But being able to chart historic footprints of islands, nearshore habitats, and potential for oyster restoration is really important to find this hard substrate. Now, this is an example of one of our airborne drones filming our mapping drone, which is also working in concert with our small boat system. And the reason we showed this to you, can you repeat that? The reason we showed this to you is twofold. We're concentrating on providing a seamless three-dimensional map just offshore of the islands and then onshore with the islands. The little boat has a LiDAR system, so in concert with the co-registered multi-beam and side-scan sonar, we have a LiDAR system to image the coastline itself, and then the airborne system we're using with a LiDAR and a high-resolution photogrammetric camera, so we can conduct three-dimensional terrain analysis of that island. And the importance is to do that the same way, with the same system, same techniques over time, so that we can examine the sustainability of a constructed island over time. And we do that by volumetric analysis of cross-sections of the island using these systems. This is just an example of the old part of Round Island in Mississippi Sound, due south of Pascagoula, Mississippi, and just a different view so that you get an idea of what we can do with this high resolution data. And we were surprised by some of our initial work. And I wanted to show you go ahead. I want to show you an example of the photogrammetric mapping camera. This camera operates at 400 feet and provides us 1.5 centimeter resolution. Turns out the photogrammetric terrain analysis capability is on par with the LiDAR system, and the LiDAR system is the best one available at this point, same one they use on Teslas. And so the photogrammetric system turned out to be just about as good, if not better, than the LiDAR in some applications. So we always have this system on our large UAV working in concert with our LiDAR as a backup, but it works just as well as LiDAR. But I wanted to show you an example of the detail of that imagery for two reasons. One, to remind you that it's a backup to the LiDAR, but secondly, the next sensor that we're going to field is a multispectral sensor with visible near-infrared and a shortwave infrared band that will fly on our unmanned airborne vehicle, and it's specifically for land cover that we'll overlay on the three-dimensional terrain analysis from LiDAR or photogrammetric camera. And this gives you an idea of the resolution of our multispectral camera as well. It'll operate at 2 centimeters, and the shortwave infrared operates at 4 centimeters. You see tracks. If you want to, you can count bird tracks with it, but we don't intend to do that. I just wanted to show you an example of the precision that we're acquiring. The bird is rock steady. The systems are working quite well, and we're excited about the addition of the multispectral scanner. And we should fly it the second week in December, so we'll stand by for that. So thank you for your time and your attention, and my contact information is on this slide. And if you have any follow-up or any further questions to ask us, please contact me, and look forward to talking with you. Thank you again for the opportunity.